The major components of our first learning target is being able to calculate potential and kinetic energy. And it's easier to split this up into two parts. First, we're going to learn how to calculate potential energy. So we have a formula where potential energy is equal to the mass of the object, the gravitational pull of your location, times the height of the object. So M stands for mass, and that will always be in kilograms. G stands for gravity, and that unit will be newtons per kilogram. And H stands for height, and the unit for height will always be in meters. In order to solve these problems, it's really recommended that you write down this variable chart. In past formulas, we've only had 2 variables, but now we're going to get into having 3 variables, and making this chart will make it easier for you to organize and be able to solve the problem more effectively. In order to solve a problem, we first need to identify the mass of the height of the object in the problem. Then, we'd write the formula for potential energy, which again is given right here. Then we'll plug in the mass and height and then gravity on Earth. In all of our problems, this is where we're going to be. And then we'll solve the problem. In our first problem, we have a 3-kilogram book sitting 1.5 meters off the ground on a bookshelf. But the first part is asking how much the book weighs. I'm sure you've noticed that the formula for weight, mass times gravity, is embedded in potential energy. So, weight is equal to mass times gravity. So we have a 3-kilogram book times 9.8 newtons per kilogram, which means the book has a weight of 29.4 newtons. Then we segue into potential energy. So I have M, and I have G, and I have H. So I wrote down my variable chart. I have 3 kilograms as my mass, 9.8 newtons per kilogram as my gravitational pull, and 1.5 meters as my height. So I've identified the mass and the height in the problem. Then I'm going to write down my formula, which is mass times gravity times height. Now I'm on the third step where I'm going to plug in mass, height, and gravity. So 3 times 9.8 times 1.5 is going to get me my potential energy. Using a calculator, you should figure out the potential energy, and that will be in joules. The second question asks, how much potential energy does a 68 kilogram person have on a 4-meter high diving board? This time we're not solving for weight first, so we're just going to dive right into potential energy. The first thing I'm going to do, like I did before, is write down my variable chart. So M, G, H. My mass is 68 kilograms, because kilograms is a unit for mass. My gravity, because we're on Earth, is 9.8 newtons per kilogram. And my height is 4 meters, because the meters is the unit for height. My second step is writing down the formula for potential energy. So potential energy is equal to mass times gravity times height. So in this particular problem, we're going to have 68 times 9.8 times 4. Again, you should pull out a calculator and determine the numerical answer, and that answer will be in joules because we're solving for energy. Potential energy is pretty straightforward. It's 3 variables multiplied by each other. Kinetic energy, on the other hand, is a little more math intensive. Kinetic energy is 1/2 times the mass of the object times the velocity of the object squared. And the reason we have speed in this particular component is because kinetic energy is the energy of a moving object. So again, MEM stands for mass, and that'll always be in kilograms. It's important to identify the velocity in the problem by itself. and velocity has a unit of meters per second. And then velocity squared, meaning you're going to take whatever number you have here and times it by itself. So this is velocity squared, and that unit is technically m squared over second squared. Do you really need to know this? No, but it's just supposed to make sense for you for right now. Our first step in solving kinetic energy problems is identifying the mass and velocity of the object in the problem. Then we'll write the formula for Ke, or kinetic energy. Our third step is plugging in the mass and velocity into the formula. Then we're going to square the speed first, which means multiplying it by itself. Then we'll multiply it by the mass, and then divide it by 2. In our first problem, we have a 1 kilogram ball and it's thrown in the air with a speed of 30 meters per second. And the question asks, how much kinetic energy does the ball have? Because I'm solving for kinetic energy, I'm going to have a different variable chart. It'll be m, v, and v squared. In my problem, I have 1 kilogram, and I know that's mass because kilograms is the unit for mass. I have v as 30 meters per second. It might be easier for you to do velocity squared first. So you'd say, okay, well, if v is 30, then v squared will be 30 times 30, which is going to be equal to 900 meters squared per second squared. Now that I've identified my two variables and actually kind of jumped ahead to solving for v squared, now I'm going to plug it into my problem. So I have kinetic energy is equal to 1/2 mv squared. So it's going to be 1/2 times 1, and then I have v squared. Now you can write 30 times 30, or you can just take whatever you have here in this variable and write down 900, or whatever your v squared value is. So then if you multiply 1/2 times 1 times 900, you would get 450 joules, and it's still joules because we're still solving for energy. In this next problem, we have a 50 kilogram boy and his 100 kilogram father jogging at 2 meters per second. What is the boy's kinetic energy, and what is the father's kinetic energy? Who had more moving energy, and why? In this last problem, we're actually doing two problems. We're going to be solving for the boy, and we're going to be solving for the father. In each of these cases, they're each going to have their own variable chart. So because we're solving for kinetic energy, we're going to need mass, velocity, and velocity squared. For the boy, he has a mass of 50 kilograms, and he's jogging at a speed of 2 meters per second. V squared means we're going to take this number and multiply it to itself, so 2 times 2, which is equal to 4. For the father, he has a mass of 100. He's running at the same speed of 2 meters per second, which means his v squared is going to be the same as the little boy, so it's 4 meters per second. Now that we've done our variable chart, now we're going to plug it into our kinetic energy formula. So 1/2 times mass times v squared. We're going to do the same thing for the father. Let's focus on the boy for right now. It's going to be 1/2 times 50 times 4, because that's our v squared. If I plug it into my calculator, I'll get a number of 100 joules. For the father, it's the same setup. We have 1/2 times mass times velocity squared. So we're going to have 1/2 times 100 times 4. If I plug this into my calculator, I'll get an answer of 200 joules. We've solved for the boy's kinetic energy and the father's kinetic energy. But our last question asks, who had more moving energy and why? Well, clearly, the father had more moving energy because the number of joules is higher. But if we look at our individual components, the reason he had more kinetic energy is because he has more mass. So to sum that up in one sentence, we would say the father had more Ke because his mass was greater. After you've done filling out this note sheet, you should move on to the independent practice, which you need to get up and grab from the front.